to this next section. Okay, diagnostic tests. Everybody takes diagnostic tests. You go to the doctor, and if you're uh, 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 he takes blood tests, he takes so on and so forth, and each one of these tests that he takes, for instance, if you are an older male, he may test you for prostate cancer. They do a PSA, protein specific antigen test, comes up with a number, represents, I guess, nanograms of some protein per something or other. I don't know, deciliter of blood, I have no idea. But it's called PSA. If you have a PSA, if you're a certain age range, a PSA over 4, they say that may be predictive of prostate cancer. A lot of different kinds of prostate cancer, some very slow developing and not much of a problem. Others that are faster developing and can be a big problem. But this is a simple test, a blood test that can be done. There's not a lot of blood tests you can do for cancers, right? This is a blood test that will help you diagnose or predict whether someone has cancer, right? Well, anytime you have a test where you're trying to predict whether a person has disease, that test comes with a caveat. And that caveat is that there's never a perfect test. Okay, the only perfect test is dead or alive. If you walk into the office, doctor's office, you're alive. If you're carried into the doctor's office, you're dead. That's the perfect test. That's the only one that's perfect. All of these other tests have situations where the test has certain values, certain predictive value. In other words, you test positive, you're not absolutely sure that you have the disease, but some tests you're virtually sure. Other tests, they use a screening test, and a lot of times they'll give you they'll indicate that you have the disease, but when they take a closer look, they use a more extensive test or more accurate test. They find maybe you don't have the disease. Why use a test that doesn't have perfect accuracy? Well, because maybe all we have, or it may be that a test that is very accurate is intrusive, invasive, or very expensive. For instance, if you go to the doctor and you're having palpitations, and he's concerned about whether or not you might have heart disease, he might do a stress test. Well, a stress test is not a very is it has some value, but it's not really the most accurate way to predict if you have coronary artery disease. The most accurate way is to do an angiogram, to put a dye in put a catheter up your vein and go all the way to your heart and release a dye and watch that dye, that radioactive dye, or radio opaque dye or radioactive dye, whichever one it is, on an X-ray and so on and so forth, and that's pretty definitive. Well, the problem with that is number one, they're dangerous, and number two, they're extremely expensive. So, a screening test, a good screening test that at least has some predictive value might be a stress test. Well, there's a lot of tests like that. I'm going to make up my own fake test, and that test is going to be test for nickel sensitivity. I'm particularly sensitive to this because I get a rash anytime I wear a stainless steel watch, and I think it's from sweating on the stainless steel back, and stainless steel has a certain percentage of chromium and nickel and so on and so forth. And nickel's a pretty popular allergy. In fact, it's getting more popular because a lot of people have stainless steel piercings and stuff like that, and they develop allergies to nickel as well. One of the components in the stainless steel, and in some forms of silver or gold or whatever. So that is a little bit of an increasing issue these days, nickel sensitivity. So let's say that we want to develop a test. We're a manufacturer of testing, and we want to develop a test for nickel sensitivity. Okay, and we don't want to expose someone to something very dangerous or anything like that, or something that we don't want to deal with something very expensive because we want to use this as a screening test. I just want to check for questions here. Yeah, I'm sorry that I kind of confused a couple of you guys because when I was looking at those Venn diagrams, I was kind of crossing back and forth over calling, referring to them as whole numbers, like 25 people out of 100 and 10 people out of 100, and kind of using that interchangeably with probabilities, percentages. 25% probability and 10%. I was trying to make it a little bit clearer. I'm sorry if I confuse some people on that, but you could use kind of either terminology. A more correct one is to refer to it as probabilities or percentages, 0.25, 0.10, 0.03, and so on and so forth. But hopefully you'll understand that I was trying to make this a little bit more real world. So if you're having a little bit of a problem understanding it, that'll make it a little bit more approachable. Okay, so let's take a look at our diagnostic tests. Okay, so now this test, let's see, we take 100 subjects. The FDA wants us to prove that this test is effective. We take 100 people that we know are sensitive to nickel. Okay, we're only looking at 100 people that are definitely sensitive to nickel. We perform the test and we find that the test is positive for 80 of those people. In other words, it predicted correctly 80% of the time that they were sensitive to nickel. That's called the sensitivity of a test. That's equal to the total number of positive tests over the total number of positives plus false negative tests. What does that mean? That means we got 80 people that we correctly said had the disease over 80 people plus 20, in other words, 100 people that we examined, and 80 of them we got right and 20 of them we got wrong. So 80 out of 100 is 0.8. This test is 80% effective. If I tested 1,000 people and that had the disease, 800 out of 1,000 times, I would correctly get a positive result. 200 times I get a negative result. That's called a false negative because they really have the disease and we missed it. Okay, now I'm going to take another control group this time of 100 subjects that are known not to be sensitive to nickel. I guess I spelled nickel wrong. How could I do that? That's pretty bad. Nickel. Let me correct that. It's annoying me. Okay, so we take 100 subjects that are not sensitive to nickel. Well, this time we find that 90 times out of 100, it correctly predicts that they don't have the disease. They got a negative result. Okay, in other words, the specificity or how good, yeah, right, the specificity of this means how good is it at predicting that the person doesn't have the disease. Okay, and that's the total number of the total number of tests we got are negatives, the true negatives, and the false. Oh, there we go. How about now? Okay, good. Somewhere I must have clicked on the mute button here a little bit. Okay, so now, not surprisingly, we're going to examine. We're going to display this data in the manner we decided to display a lot of categorical data in crosstabs. In the rows, we're going to put the exposure. In other words, what we're testing, positive or negative test. And in the columns, we're going to put whether the person has the disease or doesn't have the disease. Are they sensitive to nickel? Are they not sensitive to nickel? I'm going to start with a population that is known to have a prevalence of 20% sensitivity to nickel. Okay, that means that, let's say I sample that population, I get 1,000 people in that population. Okay, how many, if I got a 20% prevalence, how many people in this column here is all the people that are sensitive to nickel? So the bottom here is the total number of people that have a sensitivity to nickel, have the disease. if the prevalence is 20%, what is that number then out of 1,000? What would we expect that number to be? Anybody want to hazard a guess? Okay, I backed up just a little bit there. I lost you for a little bit second. Okay, it's 200. Okay, you got the right idea on the 800, but you got the wrong spot. 20% prevalence means that 20% of the people have the disease. So 200 people are sensitive to nickel, and Roberto is right. 800 people are not sensitive to nickel. Okay, and that adds up to our 1,000 people. Okay, so now let's see what you would put into these other boxes. Assuming that this test is 80% accurate, I'm going to go down here. I'm going to work on it here. Assuming that this test is 80% accurate, in other words, the sensitivity of this test at predicting someone who's sensitive to nickel is going to test positive is 80%. Out of these 200 people that have the sensitivity to nickel, how many of them are going to test positive? It's going to get 80. It's going to get it 80% right. Okay, 160, great. And that leaves 40 people out of 200 that it's going to get the test wrong. Okay, so now let's look at sensitivity. 800 people in this population, or a sample that we took from this population, don't have sensitivity to nickel. They don't have the disease. Well, what did I say? Specificity. Remember specificity, how good it is at predicting that people don't have the disease is 90%. So we're going to get it right 90% of the time. So how many people are going to test negative out of these 800 people? Okay, this one I want you to, I'm going to wait for you to give me because it's a little bit more complicated. Okay, how many people test negative? 160 is a good guess, but remember, it's right 90% of the time. Right this time is a negative test. So it would be 720, leaving 80 people in this box here, right, in the positive. In other words, that would be false positives. Okay, everybody get that? In other words, in this case, the right answer is 720. That negative test is the right answer. So 90% of the time, for these 800 people that don't have sensitivity, it's going to get a negative test, but it's going to get it wrong some of the time too. It's going to get it wrong 10% of the time, or 80 times. Okay, good. So now, how many people out of these 1,000 tested positive? Well, we got 160 people that tested positive actually have the disease. 80 people that tested positive don't have the disease. We got 240 people that tested positive. How many people tested negative? 720 and 40 is going to be 760 people. And sure enough, when you add this up, it adds up to 1,000 people. So now let's take a look at these boxes up here. Notice that this first box up here, right? I can't get them on the page together without reducing the size of this. And I don't want to do that. In fact, I'm going to make this a little bit bigger so we can see it a little bit better. Okay, this is going to be our true positives, right? And this is going to be our true negatives. In other words, you tested positive and you have the disease. You tested negative and you don't have the disease. They're right. True positive, true negative. Okay, this, you tested positive, but you don't have, you tested negative, but you have the disease. So that is a false negative. Okay, in this case up here, you tested positive, but you don't have the disease, right? So that's a false positive, right? And this number here is the total of our true positives plus our false positives. It's our total number of positives. This number down here is our false negatives and our true negatives, and that's our total number of negative tests out of 1,000 people. Okay, well, one of the things that we're interested in this is that out of this 1,000 people, we had 240 people that we told them, we think you're sensitive to nickel. We're going to send you to an allergist and have you tested further. One of the things that would be very valuable to us is to know how good a test this is. In other words, 240 people tested positive for an allergy to nickel, sensitivity to nickel. What is the probability that any of those people, that a particular person in that group, or you, let's say you tested positive, what's the probability you're really sensitive to nickel? Well, the positive predictive value, that's what that's called, is how good is this at predicting That a positive test, how predictive of it is it of having the disease? Well, a positive predictive value is going to be, let's see, only 160 people actually tested positive. Okay, so 160 people out of 240 actually have the disease. So the positive predictive value of this particular test is 160 over 240. Okay, and that would be, is that 2/3? Is that, I got that, do I have that right? Yeah, it's 2/3, right? Is 67%. Okay, everybody feels okay. Oops, 67%, or 66 point whatever, right? So 67, that's our positive predictive value. That's how likely it is that you have the disease. Now, the formula for that was true positives over true positives plus false positives, all the positives. That's how we got that 67%. Well, let's do another thing here called negative predictive value. I'm going to do it up here so we can see it a little bit better, right? Okay, negative predictive value is equal to, well, how good is it? If you got a negative test, 760 people got a negative test, how likely it is that you're really negative? Okay, well, how many people are actually negative? How many people tested negative that are actually negative? 720 people are actually negative out of 760 people that took the test, that tested negative, excuse me. So again, how was that? That's true negatives over true negatives with false negatives. In other words, how many people out of 760 that tested negative actually are not sensitive, don't have a sensitivity to nickel, don't have the disease? How good is it? How good is a predictive that test? In other words, how reliable is it for you if you tested negative? Well, chances are, probability in this particular test, let's see, 720 divided by 760 equals 90, about 95%. So if you test negative, you're about 95% certain that you don't have sensitivity to nickel. That's pretty good, right? And somebody beat me to it there. Of course, one of you guys beat me to it. Okay, so that's the formula for that as well. Now, let me think about this for a second. What am I looking at here? What is positive predictive value? The positive predictive value is the probability that you have the disease given that you tested positive. What does that sound like to you? I'll say that again. The probability that you have the disease given that you tested positive. What kind of probability is that? It's a conditional probability. That's one of the reasons why we're so interested in conditional probabilities. Okay, negative predictive value is also a conditional probability. And as we go on in time, maybe we'll get a chance to show you some more elaborate ways to apply these conditional probability formulas to test this stuff. I want to show you one other thing in the last few minutes here. I want to show you one other thing that has an important influence on diagnostic tests. Okay, positive predictive value is 67%. In other words, 67%, if you test positive, there's 67% chance that test is right and you really have the disease. Well, I'm going to take a look at another population. It's the same test. The sensitivity is 80%, specificity is 90%. Nothing's changed as far as the test is concerned. What's changed is the population. This population only has a 1% prevalence of nickel sensitivity. So if only 1% of the population, we sample 1,000 people, if only 1% of the population has a sensitivity to nickel, out of that 1,000 people, what's 1% out of 1,000? 10 people are sensitive to nickel. That leaves 990 people not sensitive to nickel. Okay, the test is 80% sensitive. So out of those 10 people, how many people actually test positive correctly? Somebody tell me. Right? It's going to be 8. Exactly right. And 2 people are going to be false negatives. They're going to test negatives even though they have this. Okay, not sensitive. Okay, got to get my calculator out for this. It's not going to be that easy. Not sensitive. Well, this where specificity is 90%. So how many people are going to how many people are going to correctly test negative at a 990? Well, 90% of those 990 people are going to correctly test negative, true negatives in that box. 990 times 0.9 is 891. 891 correctly test negative. So out of those 990 people, how many tested positive? Okay, even though they didn't have, well, 10% of that 990 or 99 people test positive. Got it? Everybody agree with that so far? Okay, 10%. If we add those together, they end up in 990. 90% of the time we get it right, the negative test, but 10% of the time, people that don't have the disease test positive. Nothing on the test has changed. Only thing that's changed is the prevalence of the disease in the population. Okay, how many people test positive? 99 and 8 is 107. Negative is 893. I'm not going to bother with negative predictive value. Let's look at the positive predictive value of this test. It's going to be the number of people that are positive that test positive out of the total number of people that test positive is 107. Out of those 107 people that test positive, only 8 of them are correct. It's the same test. Nothing's changed in the test. So what is that equal to? I'm going to say that's equal to roughly, I'm going to call it 7%. It's a little bit more than 7%. I'm going to say 7%. In other words, if you take this test, which is 80% sensitive and 90% specific, because the prevalence is so low, when you have a low prevalence like this, you're testing a lot of people that don't have the disease, so you get a lot of chances to make a mistake. Your positive predictive value goes from 67%, only 7%. Well, what does that mean? That means that tests that you do, diagnostic tests that you do on population, when you test a whole population, for a disease, you do a lot of tests. You get a lot of chances to get it wrong. So the lower the prevalence is in the population. So you get diseases like uh, 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 um, uh, prostate cancer, diseases like you can come up with some others for me, I'm sure. Uterine cancer, pap smears, for instance, right? When you're these are diseases that are have relatively low prevalence in the population, but we test a lot of people. So there's a lot of controversy about testing a lot of people. And if you go online, there's a couple of links I put on there. I don't know if they're still active, but if you go on there, you find a couple of articles that review this. For instance, prostate test, that test I just told you about, that PSA, if it's over 4, immediately get sent to urologist to get, further examined and stuff like that. It's only in the range of 4 to 10. It's only 30. The positive predictive value is only 30%. So 70% of the people that get sent to urologists do not have cancer, but they do wind up going through a bunch of more expensive and rigorous tests and so on. And some of them even biopsies that are, not the most pleasant things in the world for prostate cancer, so or safest things either. They wind up, with either more expensive procedures or invasive procedures based on a test that that winds up giving you a lot of false positives. Okay, so keep that in mind. Prevalence of the disease in the population has a big impact on the positive predictive value. Okay, any questions? That's more than enough for tonight. I went over just a few minutes. But are there any quick questions there, anything like that? Thanks for tuning in.